Okay, hello and welcome back. This is going to cover section 2.2, the graph of a function. So see some attributes of graphs of functions specifically, and then what kind of information we can obtain from the graph. And we'll do a little bit of functional analysis. So just as a reminder, a function is a relation that relates some input to one specific output. We usually think about x and y, but it could be anything in general. And the key point is that there's one specific output for any given input. So I mentioned last time, we can look at a graph and think about a vertical line going through the graph. And if it touches the graph in more than one position, then it's not a function. That would coincide with having multiple outputs for some given input. So that's what we're calling the vertical line test. As a set of points in the xy plane is the graph of a function specifically if and only if, that's a specific kind of statement, meaning like that's the only condition, every vertical line intersects the graph in at most one point, and it needs to be every single possible vertical line. There may be some places on the function where it only intersects once, but if there is even just one location where it hits more than one time, then it is not a function, and you would call it a relation instead. So a couple quick examples. This first graph is the graph of x squared. It's a standard parabola centered at the origin, and they have some vertical lines, and notice anywhere we could possibly draw one, it would only hit the function in one particular spot. So in that case, that is a function. Looking at x cubed, thinking about drawing vertical lines, anywhere we draw it, it's going to hit it in only one place. So also a function. C is x equals y squared. So this is it's like a sideways parabola. Instead of x being squared, y is squared. And then yeah, notice vertical line hitting the function in more than one position. So not a function. And then D is our unit circle, a circle centered at the origin with radius 1, and also vertical line hitting the function in more than one position. So not a function. So it's a pretty simple test if you have the graph available to you. Sometimes you don't have the graph and you're just looking at the equation, but notice what these two have in common. In both of these cases, the y variable is squared. And if you remember last time, one of our tests, like let's look at C for example. We have x equals y squared. If we were to solve this for y, we have to take the square root of both sides. And when we do that, we have to introduce this plus or minus. So y equals plus or minus the square root of x. That plus or minus produces two outputs. And so that breaks our definition of a function. So one thing you can do if you're just looking at the equation is look out for even powers on your y variable. It produces that double output. If you have the graph, then even better. You can just use the vertical line test. So in part 2 here, they're having us obtain information from or about the graph of a function. So here's the setup. We're looking at this graph here. So it says, let f be the function whose graph is given in figure 19, And they give us some context. They say the graph of f might represent the distance y, excuse me, that the bob of a pendulum is from its at-rest point at the time x. It says negative values of y mean that the pendulum is to the left of the at-rest position, and positive values of y mean that the pendulum is to the right. So just to give some context, imagine we have a pendulum and the at-rest position would be as it's just hanging. And then we can imagine this pendulum is pulled back and it swings maybe to some maximum position. And they're calling this where y would be positive. And then it swings back and goes in the other, maybe some other maximum position. And this is where they're saying y is negative. And then it swings back and forth. So it's some kind of repeating motion. So you can see that represented here, it's pulled back to some maximum position, and then it swings down, and at 0 here, this would be like this at-rest point. And then it goes down to this negative position, so that would be this maximum here. But then gravity pulls it back to the middle point, and then back to the maximum point, back to the minimum point, and so on. So we see some periodic motion. All right, so just got some context here. So if we have the graph, we can try to extract some properties of this particular graph and of this particular system. So let's see what it's asking of us. The first question asks in part A, what are f of 0, f of 3 pi over 2, and f of 3 pi? So f of 0, remember from our last video, this is function notation, meaning that f is the name of our function, and 0 is what we are inputting into the function. So 0 would be our x value. So if we have the graph, you can look at where x is. So if x is 0, it would be here. So the output is where the graph exists, or you can just see it as the y value. So the y value when x is 0 is this point here, 4. So we can say f of 0 is equal to 4. F of 3 pi over 2. 3 pi over 2 is our new x value. So we look at where that is on this graph. I see 3 pi over 2 here, and the output is 0. That means it's back at one of that middle point. And then f of 3 pi. Look at where 3 pi is on the x-axis, it looks like right here. And the output is negative 4. So if you see this kind of notation asking f of some number, it's asking you what is the output given that particular input. So pretty simple. So B asks, what's the domain of f? And recall the domain is the set of all of the inputs of our function. Specifically, all of the inputs for this specific situation. So if you have a graph of a function, you can just look, our inputs are our x values. So just look at the range of x values in which the graph exists. So what's the smallest x value? Now there's no like arrows here that are showing that the graph is continuing forever. If you see a little arrow at the end, that might indicate that the graph is going, and then I might say, well, that's going all the way to negative infinity. So that's not the case here. It's just starting at this specific location. Because in this case, we're saying x is time. So we're starting at time 0. So it's starting at 0. And then it looks like the system stops here at a time of 4 pi. Kind of a strange way to call time, but it's just a value. Maybe you get some decimal point. So that would be the maximum x value that we have. And our other possible x values are all values in between here. So we can say that the domain, using set builder notation, all values of x such that x is greater than or equal to 0 and less than or equal to 4 pi. That's one way to say it. Or using interval notation, we can just say the interval from 0 to 4 pi, including both endpoints. So just as a quick reminder, in interval notation, if we're using the brackets, that means we are including endpoints. And if we're using standard curved parentheses, that means we do not include endpoints. C is asking for the range of the function. So the domain is the set of all of our inputs. The range is the set of all possible outputs. So instead of looking across the x-axis, we would look across the y-axis. Where does it start? And so for domain, start from the left and go to the right. For range, start from the bottom and go to the top, because you want to start at the minimum y value, or the minimum output, and then end at the maximum output. So it looks like the minimum output, like this, in this case, this is like the farthest to the left that the pendulum would swing, is down here at -4. And then the maximum possible output is up here at +4. So we just want to describe that range of values. So in set builder, we could say the set of all values of y such that y is between -4 and +4. Or an interval notation from -4 to +4, including our endpoints. So D is asking to list our intercepts. And it says, recall that these are points, if any, where the graph crosses or touches the coordinate axis. So in this case, they're looking for both the x and the y intercepts. So I see we have one here. And then also here's our x-intercepts. This is where you're crossing that middle point in the pendulum swing. So we have this one y-intercept and then our 4 x-intercepts. So let's just list them, and it wants them as, well, let's list them as coordinate points. So we have the point 0, 4, the point pi over 2, 0, the point 3 pi over 2, 0, the point 5 pi over 2, 0, and the point 7 pi over 2, 0. So it's pretty nice when we have the graph, because we can just look and pull this information from it. Okay, let's look at E. E asks, how many times does the line y equals 2 intersect the graph? Well, the line y equals 2. Keep in mind, y equals something is a horizontal line. So y equals 2 is the horizontal line going through 2 on the y-axis, meaning y is always equal to 2, x can equal anything. So we're just counting. How many times does it cross? Well, 1 time, 2 times, 3 times, 4 times. So how many times does the line y equal 2 intersect the graph? 4 times. You can just visually inspect and see. And then f. For what values of x does f of x equal -4? So this is saying we have some output as -4, and we're trying to find what values of x, what input values give that particular output. So one way you can do that, just like in our last one, we can think about a line going through -4, and where is it touching? Looks like at those 2 points. So we can say f of x equals -4 when what? When we have these two inputs, either pi or 3 pi. So we can say when x equals pi or x equals 3 pi. So pretty simple so far. This last question is a little bit more interesting. It asks, for what value of x is f of x greater than 0? What does this mean? It means for what inputs is the output positive? So that means that we would be above the x-axis. So for what values of x is our graph above the x-axis? Well, we have sort of a bunch of sections. We have this section here, positive. We have this middle piece. And we also have this end piece. So we have 3 distinct regions, or 3 intervals, where our function is positive. So we just need to list them out and combine them together. And we're talking about intervals of x values. So we can say this first one starts at an x value of 0 and then goes until the x value of pi over 2. So it's definitely, the function is positive when we're starting because it starts at +4. So I'll say f of x, our function, the output of our function is greater than 0 or is positive. I'll say on these intervals. So starting at 0, I'm going to include the endpoint because at that point the function is positive. And then we're going all the way until pi over 2. But at pi over 2, the function is equal to 0. So I don't want to include that endpoint. I'll use the curved bracket. Then our next interval, we skip a spot and then we start at 3 pi over 2. So the next one starts at 3 pi over 2. I won't include it because it's 0 at that point, and then it goes until 5 pi over 2. Also won't include it. And then we join these two sets together with the union, this big U. It just means that you are you're combining the two sets together. A union of two sets. So then we have our third region, which starts at 7 pi over 2. Again, I won't include the endpoint because it's 0 there. And then it goes until 4 pi. And this time I will include the endpoint because notice at 4 pi the function has a positive output value, just like where we started. And we'll join this with our other two, also with the union. Yeah, these are set operations. You may have done a little bit of set theory maybe in an algebra class, You'll probably think about them in terms of probability and statistics. You might use some set theory there, or it might come up in other contexts. So this is when we have the graph of a function. It's pretty easy because we just need to look and interpret and just be careful about how we're stating our answer. But how about when we don't have the graph, we just have the equation and we need to like infer something about the graph. And maybe we can use those points to try to graph it. This question and the one before, this is like some functional analysis. Meaning that we're given a function and we're describing some attributes of it, maybe the domain and range, maybe some maximum or minimum values. If you are maybe doing some physics or trying to build a mathematical model of some real world situation, then these particular points have some interesting context. And you might want to try to find out where they are or what inputs will produce a certain output that you're looking for. Think about like financial math. Maybe you have a model of a stock price. You're probably interested in where some minimum and maximum points are. Maybe the range of possible output values. So let's look at this example. We have our function f of x equals x plus 1 over x plus 2. This is a rational function because we have a fraction or a ratio and we have x's in either the numerator and the denominator. So our first question is asking us, what is the domain? And remember from our last video, for domain questions, we're typically looking for, are there any values that will force us to divide by 0? Or are there any values of x that will cause us to have a negative value underneath the square root if there's roots involved? So for rational functions like this, we have that first case where we have some x in the denominator. So our function f is undefined for any values of x that makes us divide by 0. So that makes the denominator equal to 0. So recall, we can just set up a little equation. Well, okay, I want to make sure that x plus 2 is not equal to 0. This is a very simple example. You can probably just look at it and tell, oh, well, x shouldn't be equal to -2. But it might be more complicated. Maybe you have a quadratic or something and you have to set it equal to 0 and factor and solve. There might be a few values of x that would make it equal to 0. So just something to keep in mind. If you can't tell just by looking at it, set up a little equation like this and solve it. We can use those algebra skills to our advantage. So the domain, you can say the domain of f is set of all values of x such that x is not equal to -2. Or if we had to use interval notation, we're saying everything except -2. So we can say from -infinity until -2, but not including -2, and join it from -2, not including -2, up until positive infinity. So we're like skipping over that -2. And just in case you were wondering, with infinities, negative and positive, the practice is to use the curved brackets, since you wouldn't say you include infinity. It's not a value. It's more of a concept, so we can't really wrap our arms around it. It'll just keep going forever, so I tend to use the curved bracket. So again, as a reminder, this is set builder, and this is interval, in case the homework asks you for a certain kind of expression. So how about part B? They say, is that point on the graph of x, is the point 1 comma 1/2 on the graph on f? Well, we don't have the graph with us, so how can we know? Well, we can test it algebraically. What this statement is saying, this point is saying that an input of 1 produces an output of 1/2. Or another way of saying that is f of 1 should be equal to 1/2. Well, we know what f of x is defined as. We have the equation, so we can just test this. We can try plugging in 1 and see if we can get that value of 1/2 as our output. So let's find out. F of 1, remember this is our function here, so let's plug in 1 for x. Well, that would be, instead of x, plug in 1 plus 1 over x plus 2, so 1 plus 2. So 1 plus 1 is 2 on the top, and then 1 plus 2 is 3. So this tells us that f of 1 is equal to 2/3, not equal to 1/2. So we'll have to say no, that point is not on our graph. And they told us this was a function, so we know that each input should only have one specific output. So for this input of 1, it can only have one possible output. So since we know that the input of 1 produced 2/3, it's not, this point will not be on the graph. Okay, part C. It says if x equals 2, what is, if x equals 2, what is f of x? Well, that's just saying, what is f of 2? X equals 2, so what's the output? Well, we just need to plug in 2. So that would be 2 plus 1 over 2 plus 2. Or 3 over 4. But it's asking us what point is on the graph. So let's list it as a coordinate point. Our input was 2, that's our x value, and our output is 3/4. Part D. Now they're saying if f of x equals 2, what is x? Meaning that our whole function, for some value of x, we get an output of 2. So what value of x gives an output of 2? Well, we can just set our function equal to this value and then solve for x. If f of x equals 2, that means x plus 1 over x plus 2 is equal to 2. And we just need to solve for x now. So let's multiply the x plus 2 over to the other side. That means x plus 1 equals 2 times x plus 2. So x plus 1 equals 2x plus 4, distributing the 2. Now let's combine like terms. I will subtract this x over to that side. Let me do that first. So 1 equals, instead of 2x, I'll just have 1 left. x plus 4. So then I'll subtract the 4 over to the other side, so negative 3 should equal x. So that means our input is negative 3, and then our output is 2. So we'll have the point negative 3 comma 2 is on our graph. So you might be asked to plug in a value when x equals a certain value, what is f of x? Or they might tell you what f of x is equal to, and you need to sort of backtrack and solve what input value produced that output. what x value produced that y value. All right, I think there's one more. So E says, what are the x-intercepts of the graph, and what are those corresponding points? So I'll write our function again. F of x is x plus 1 over x plus 2. So we want to find the x-intercepts. Remember that x-intercepts occur when y equals 0 on an xy plane. So we can say x-intercepts occur, to use function notation, when f of x is equal to 0. When the value of our function is equal to 0. So just like in our last one, we can just set it equal to 0. Let me just go ahead and write it out. So we can say x plus 1 over x plus 2 is equal to 0 and solve for x. So let's do a similar thing. We'll multiply the denominator over. It's going to be multiplied by 0, so it basically just disappears. It'll become 0. So x plus 1 equals 0. Therefore, x equals negative 1. Meaning when our input is negative 1, we get an intercept. The output is 0. So that means at the point negative 1, 0, our graph will be crossing the x-axis. This is the intercept, specifically the x-intercept of f. Intercepts typically have some particular significance, especially when they're applied to a specific situation. And they don't ask for this here, but if it was asking for the y-intercept, well, y-intercepts occur where x is equal to 0, so you just want to find f of 0. Plug in 0 for your x's. In this case, you can see we would get the point 1 over 2. So we'd have the point 0, 1 half should be on our graph. It's a very common thing that a question will ask you. What's the domain? What's the range? What are the x and y intercepts? Later on, we'll probably discuss increasing and decreasing behavior as well. All right, let's look at our last example. This one, it has an application. A little space here. So it says for an individual walking, the energy expended, E, in terms of speed, V, so velocity, can be approximated by this equation. It's an approximation, so it's not exact, but it's close enough. You're kind of forced to do approximations a lot of times in application. So we have this equation, and it's asking, first, find the energy expended for a speed of v equals 40 meters per minute. In other words, it's asking us to find E of 40. Okay, simple enough. We just need to plug it into our formula. 29 over 40 plus 0.0053 times 40. Just plugging it in for each v in the equation. So if you plug this into a calculator, you should get rounding to 2 decimal places, 0.94. And this output is in calories per minute per kilogram. For B, find the energy expended at a velocity of 70 meters per minute. Well, that's the same thing. So V is equal to 70. So we're finding E of 70. So just plugging in 29 over 70 plus 0.0053 times 70, which, plugging that in, is approximately 0.79 calories per minute per kilogram. Which is interesting. Think about the implication here. It's saying as you're walking 40 meters per minute, you're expending more energy than you are when you're walking 70 meters per minute. Kind of strange. Maybe it takes more energy. Maybe once you're walking at a certain rate, you have some sort of momentum. It ends up being less energy. And then in part C, it says find the energy expended when V equals 100 meters per minute. So we're finding E of 100. So that's 29 over 100 plus 0.0053 times 100. Plugging that in, you get approximately 0.82 calories per minute per kilogram. So it's going back up. It's like there's some higher amount, then it dips down, and then it goes back up. So we can imagine there's some kind of minimum that we could potentially find. So that's what this question, the remaining parts are asking you. They have you graph it and create a table to find the value that minimizes the energy. So I went ahead and graphed it in Desmos. If you've used Desmos before, let me bring this up. I'll just scroll down. And if you just type it in, it's hard to see the upward curve, how it goes down and goes back up. But if you mess with the scaling of the X and Y axis, you can see that behavior. It has some initial high point, but then it actually decreases as it speeds up, as you speed up down to some possible minimum point, and then it starts to increase again. And if you zoomed out a bit more, you would see this graph increase. So it's an interesting result. And in Desmos, it'll give you the minimum point, and it occurs somewhere around here. It's around the 0.7, we're at 74 for our velocity value. So pretty interesting results. This is an example of finding a minimum value of a function, which is something that is usually of interest. And it's something that you can do mathematically once we gain some skills in calculus. For now, we'll have to do some estimation, maybe plotting the graph and visualizing it. So some interesting results. Okay, this was a quick section. This was 2.2, looking at the graph of a function. So we identified the graph, when a function is a function, based off of the graph. Remember, that was the vertical line test. And then we did a little bit of light functional analysis by obtaining some information from or about the graph of a function. All right, that'll be it for this video, and we'll see you next time.